This video is part 2 of section 10.4, Hyperbolas. And on the last video, we left off on this problem, example 5. I had to stop recording. So let's continue now. So I'm going to read the problem again. We have two microphones that are a mile apart. And let's look at the two microphones. They will actually be in this drawing. The microphones are the foci or foci. There we go. And so because we know that they are 1 mile apart from each other, so the distance from one to the other, it is 1 mile. So we're going to use the conversion of 1 mile is equal to 5,280 feet. And we do that because we're also going to use the speed of sound, and that is given in feet per second. So the microphone A receives the sound 2 seconds before microphone B. So the foci on the right is microphone A, the one on the left is microphone B. And we have that 2 seconds. So it says, where did the explosion occur? And so as you could see, the microphone from this side, A, received the sound before, because, and now we know that the explosion actually occurred here. That's what that drawing means. And it took for them to receive, for microphone A to receive that sound. We don't know exactly how fast that was, but we know that that distance is the same as this distance. And then the extra 2 seconds, that is the space that we see highlighted here. That's the extra 2 seconds. Now, we're using the, we're assuming that that sound travels at 1,100 feet per second. So if we're talking about 2 seconds, then that was 1,100 per second. So we say 2 seconds times 1,100, and that is why we get 2,200 or 2,200. So that is how we get the distance that we have right there. So based on that, I'm going to go to the next slide, but we will come back to that one. So we position the point representing microphone A, and I don't know, because the problem does say 2,200. So I don't know why we're doing that. Oh, yes, I know why. Okay, so let's not go to the next slide yet. So remember, for the distance between the foci, it's actually, we use the equation 2c equals, and then we're going to get this part right here. We said already that they were a mile apart. And so with that, we could solve for C, and that will be 5,280 divided by 2. So C will be equal to 2,640. So that distance is the distance from each microphone to the center. So that means that from that center to this microphone, we have 2,640. And same thing from the other microphone to the center, 2,640. However, the distance that we're discussing, that was that caused the delay of the 2 seconds for this microphone B to detect the sound, that was the 2,200. So if we were to take this line right here, let's use a different highlighter. So if we were to consider that distance and put that distance here, the same, that's what will be the 2200. But the distance from the microphone to the center of the hyperbola will be there. And I know here we can only see one branch of the hyperbola, so I'm just gonna like try to sketch the other one. It won't be like very accurate, but it will give you an idea so you remember what type of conic we have. So it will be like something like that. Those are the two branches. Perhaps this one a little more that way. Okay, so now that we know the value for C, we are going to go ahead and try to find A. And so for A, we are going to use the equation that says that 2A is equal to 4,400. So then if we divide that by 2, oops, then we will get the 2,200. So what we are assuming is that the distance between the center and the foci, and not the foci, but the vertex, it's gonna be the 2,200. Now it's probably, I don't think it will be, that will be the case. I think it's more, okay, I'm gonna pause the video for a second and think a little bit. Okay, so what I'm thinking is that the distance that we have from the center to the vertex, to one of the vertices of the hyperbola. So that is what we called A. And the one that we have from the center to the foci is what we call C. So to find the distance from here to here, the one that I'm marking in green, that will be equal to C minus A. So if we continue on that way, and we use the same distance from here to here, that would also be C minus A. And then we also have the 2,200 right here. So the whole distance combined will be the 2,200 plus 2 times this, the C minus A, C minus A. And that is equal to the 50 to 80, the 1 mile. Remember, they are a mile apart. So if we solve for A right here, we could do it that way, because we already know the value for C. So if we just leave here C minus A right here for now, and we take the 5280, subtract the 2200, we get 3080. And so right here, if I go ahead and distribute, or actually I will do this. I will not distribute. I will just take that 2 that is multiplying and divide down here. So we're going to have that C minus A is equal to 3080 divided by 2, and we get 1540. So if we want to find the value for A, we could say C is equal, we found that here, to 2640. We could take this negative A to the right side, so that is positive A. And we can take this positive 1540 to the left, so it's over here. And I don't think this is going to work, actually. So I got that A is 1100. That's not good. Oh no, actually, yes, it is true. It is true. It is 1100. Oh, okay. So then let's go ahead and erase this part. So yes, this was the correct way to find A. So now we have that C is equal to 2640, and we have that A is equal to 1100. Okay, perfect. So now that we know A and B, I'm sorry, C and A, we could find B. And let's do that on the next slide. So for B square, we're going to use the equation C square minus A square. So if we substitute here C square, that will be 2640 square minus 1100 square. So of course, if we want to solve for B, we'll have to take the square root of those numbers. And I'm actually just gonna enter everything at once on the calculator. And so from there, we get approximately 2399.92. So let's just go ahead and round it to 2400. We're very, very close to it. Okay, so now we have all of them. We have A, we have B, and we have C. So to write the equation, and we're just going to assume that the center was at 0, 0. So then the equation of our hyperbola, and we could see that the transverse axis is the horizontal axis, so my x squared goes first, then my y squared, and then of course we want it to equal to 1. So then here on the bottom, we're going to have A, which we found it to be 1100, but square. And then we're going to have B here, but square. And notice that B is larger than A. That's fine. A is the one that comes with the first fraction, the one that has a positive sign in front of it. So if we just calculate 1100 square, we're going to get a pretty large number. So is going to be 1, 2, 1, and 4 zeros. And the other one is going to be 2400 square, and that would be 5, 7, 6, 4 zeros. So that would be like 5,760,000. And the other one is 1,210,000. So that's the answer. That's the equation for that hyperbola. And going back to the question was, where did the explosion occur? So the explosion occurred somewhere on the right branch of the hyperbola. That's the answer. But of course, you know, those problems, sometimes you have to enter the equation. So that is the equation, and the answer is on the right branch of the hyperbola. So that is the answer. So we're almost done with this section. I know it's pretty long. Oh, well, that is actually, we had some space to calculate that. And oh, that's another way to calculate A. 2A equals 2200. So if we divide by 2, we will get the 1100 that we did previously. So, and that is how to find B. And so we already got that answer. We can skip those slides. So another interesting application of conic sections, it involves orbits of comets in our solar system. And not all of them go in a circular or elliptical way. Some of them have parabolic or hyperbolic orbits. So out of all these comets identified prior to 1970, 240 had an elliptical orbit, 295 had a parabolic orbit, and 70 had a hyperbolic orbit. You could see those represented here. That's a hyperbolic orbit. And then here we have the parabolic. And then we have the elliptical orbit. The center of the sun is a focus of each of these orbits. I think that's so interesting. And each orbit has a vertex at the point where the comet is closest to the sun, as you can see on the figure on the right side. There have been many comets with parabolic or hyperbolic orbits that were not identified. We only get to see such comets once. Comets with elliptical orbits, such as Halley's Comet, are the ones that remain in our solar system. So to find one of the applications is to find the velocity of the comet at the vertex. And so if P is the distance between the vertex and the focus in meters, and V is the velocity of the comet at the vertex in meters per second, then the type of orbit is determined as follows. So to figure out if it will be an elliptical orbit, parabolic orbit, or hyperbolic orbit, we use this comparison. And so you could see for all three of them is the same formula, but what we compare is if that value that we get will be greater than the velocity or equal to the velocity or less than the velocity. And so for all these relations, M, uppercase M, it is the mass of the sun, and you could see it there. Also for G, G is right here, and it represents the cubic meter per kilogram second square, and that is a universal gravitational constant. So that is what G and M are. And remember, P is the distance between the vertex and the focus. The textbook didn't have an example of of using those formulas. So I don't think I gave you one of those on the homework, but um, if you have a question like that, feel free to reach out and ask for help. All right, so this is the very last thing of this section, and it's very easy, very simple. So I mentioned this from the beginning that we have general equations, but we also have standard equations. So we've been working on how to find the standard equations. So now it's time to get to the general equations. So those are the ones that, first of all, you have one side equaling 0, and you have everything else on the other side of the equal sign. So you can have an x square, a y square, an x to the first, and a y to the first, and then f represents the constant term. So in this case, we don't have a b, sorry. A, C, D, and E, and F are numbers. They're just real numbers. So what we're going to be comparing is A and C. So for A, the coefficient of x squared, if A is equal to C, then we will know, provided they're not 0, we will know that we have a circle. That's all we have to compare. For a parabola, we take the product of A times C, and if that gives us 0, then we have a parabola. Now, if we do that same product, and we get a number that is positive or greater than 0, a positive product, then we know we have an ellipse. And if the product happens to be negative, then we have a hyperbola. So those are the 4 cases that we're going to work with. So the test above is valid when the graph is a conic. The test does not apply to equations such as this because that wouldn't be a circle. The equation of the circle would have been to have a square here, which, I mean, you can't even have a negative radius, but if this was just a positive one, then yes, we will have a circle. In fact, the unit circle, the one that we started this course with, the circle with the radius of 1. So this one with this being negative is just like nonsense. So let's go ahead and move on to the next slide and last one. So we're gonna check what they are. So for let's go to the very last one, and we do have the answer here, but let's see why. So if we compare A and B, you could see A is a 2, B is a 2. So because they are the same, A equals, and it's not, I keep calling it B, I should call it C. A equals to C, so then we have a circle. Let's look at the other 3. So if we multiply, so we have to find A, in this case A is a 4, and then we have that C, the coefficient of C is always the coefficient of the y square, as you can see here. And you could notice here that we don't have a C square. So we have a 0. So if we multiply A times C, we will get 4 times 0. So AC is equal to 0. Therefore, we have a parabola. Now, next equation, we have A is equal to 4, and C is equal to -1. You see that negative in front of it? So that means the coefficient is -1. And so if we multiply A times C, it will be 4 times -1. Now, since this is a -4, we know that AC, the product, is less than 0. So what happens when your product is negative or less than 0? You get a hyperbola. And then finally, same steps, we take A multiply it by C, and that will equal A in this case is a 2, C is 4 positive, so the product AC is 2 times 4, which is equal to 8. So we know for a fact that AC is greater than 0, it's a positive number. So then we have an ellipse. And this is the end of the video.